Wouldn't it be nice if all your problems just canceled out with each other? Well, lucky for you, today is your chance to do that. In telescoping, you can form a giant complicated expression. Everything just cancels out and you're left with something super simple. Let's see an example of telescoping in action. Okay. Evaluate 1 squared minus 3 squared plus 5 squared minus 7 squared, so on, until plus 2009 squared. And then minus 2 squared minus 4 squared plus 6 squared minus 8 squared, all the way till plus 2010 squared. Doesn't this seem like a really gnarly expression? Well, thanks to you, we can do telescoping. Everything will cancel just like that. Okay, so how do we get stuff to cancel? I mean, there's no way we're going to evaluate 2010 squares. That's not feasible for us. So we've got 1 squared minus 3 squared plus 5 squared, so on. And then we've got minus this expression. So we can write that as minus 2 squared minus 4 squared, that's plus 4 squared, minus 6 squared, right? Because minus 6 squared, and then minus 8 squared, right? Minus 8 squared, so 8 plus 8 squared, and so on, right? It just alternates signs between both expressions. And this goes all the way till minus 2010 squared, right? Minus 2010 squared. And then the first expression goes all the way till simply plus 2009 squared. So telescoping will hopefully allow stuff to cancel, but how should we cancel? I mean, there's just way too many terms that are just flying around. Okay, so the trick here is what we're going to do is we are just going to pair these terms together. So let's, for example, pair these two terms. 1 squared minus 2 squared. So now, that's just the same thing as negative 2 squared minus 1 squared, right? What is 2 squared minus 1 squared? 3, of course, but we don't want to evaluate each expression because once we get to these larger numbers, that's not easy. Instead, can we rewrite it maybe? Does this look familiar? Any identity maybe? Maybe have you... Yeah, you know, it's different. You know what I'm talking about. It's difference of squares, of course. Because there's difference of 2 squares, we factor it like that. Okay, now what about this part? That's just plus 4 squared minus 3 squared. And by difference of squares, that's, well, it's just going to be 4 plus 3, 4 minus 3. Okay? And the thing is, we can continue on with this, but the key thing to note here is that this term is always 1. 1. So next time we would have minus, right? This would be minus 6 squared minus 5 squared, because it's 5 squared minus 6 squared, which is the same as 6 squared minus 5 squared, the negative of that. And this is just minus 6 minus 5 times 6 plus 5. Notice here, 1, 1, 1. Those are all 1. So it seems like to evaluate this, it's just going to be the same thing as negative of 3, then plus 7, then minus 1 times 11, plus 15, so on, all the way till we get to 2009 squared minus 2010 squared, which is the same thing as negative 2010 squared minus 2009 squared. Difference of squares, 2010 minus 2009 times 2010 plus 2009. Whoops, looks like we ran out of room there. But you understand it's going to be a 9 there. Squared. Sorry, I couldn't write it in. And that is the final term of the expression. Let's just move that a little bit, you know. The power of not having to use pencil and paper. And then that becomes plus 2009, right? And then this is just 1, of course. So we're just left with minus 2010 plus 2009. That's minus 4019. Okay. We've already telescoped a lot. I mean, a lot of terms of... Basically, we've simplified these giant squares into something nice and simple. But we're still not done telescoping. Parallel scoping Stage 2. How can we telescope now, you might wonder? Let's notice here, like the first thing to do in telescoping is always, figure out a pattern. That's the first step. Dot dot dot, and then plus 4015, right? Notice how it's negative 3, 3, 7, 11, 15. It's increasing by 4 every time. But then the sign is alternating. Negative, positive, negative, positive, positive, negative. It always alternates the sign. So what we can actually do here is notice that 7 minus 3, that's 4. 15 minus 11, 4. Is every pair of these terms just going to be 4? So positive minus plus 7 minus 3 plus 15 minus 11. Let's write a few more. I know I only wrote a few here. There's minus next term. What will the next terms be? Minus 19 plus 23, 4. All the way until minus 4011 plus 4015 with a bunch of terms in between, of course. And this is also 4. And then we've got just a straggling negative 4019 on the outside, which is just separate. You can think of it as extra part. So each of these terms is 4. 4, 4, 4, 4, and a bunch of 4s in between. But the question is, how many 4s are there? I mean, we need to figure that out, don't we? So to do that, let's first explore how many such terms we had originally in the sequence. Oh, my head is locking. Sorry. Okay, so notice how many of these square terms do we have? Notice how it includes all the numbers from 1 to 2009, all the odd numbers. And if you remember the arithmetic sequence video, the number of terms in an arithmetic sequence with first term 1, last term 2009, and common difference 2 is just 2008 divided by 2 plus 1, which is 1005, right? There's 1005 odd numbers between 1 and 2009. So there's 1005 terms in this sequence. And there's also 1005 terms in this sequence, right? Just all the even numbers from 2 to 2010. That's 1005. And therefore, there must be 1005 of these kind of terms here. Because we're just subtracting, adding adding these expressions together. So we've got 1005 of these terms over here. But then notice how we're pairing two of them together. And we've got one straggler. And that means that out of these 1005 terms, 1004 of them pair together into 1004 divided by 2 equals 502 pairs. So 502 pairs that equal 4. 502 times 4 minus 4019. 502 times 4, that's 2008. Minus 4019, that's negative 2011. And that is our answer. A classic application of telescoping where the key idea is to write this as like that, and then notice this kind of 1 squared minus 2 squared. Oh, we can rewrite it. Difference of squares, it forms something nice. 3 squared minus, or 4 squared minus 3 squared, it forms something nice as well. And then we kind of cancel it out using difference of squares to get nice and simple expression like that. I mean, it's not simple yet, but it's much simpler than this, if you ask me. And then after that, we used some term counting with arithmetic sequences and saw that 1004 of the 1005 total terms pair up, 502 pairs of 4, and then one straggling negative 4019 term on the outside. It all cancels. A classic application of telescoping. Key ideas: look for a pattern, look for terms to cancel. Let's explore another problem. Find 1/6 plus 1/12 plus 1 over 20. I'm not even going to say the rest, all the way till 1 over 72. So there's one way to solve this problem, and that's to find a common denominator and do the computation. And I'm not interested in doing that in this video. I don't think any of you are interested in doing that as well. It would be really, really messy. Maybe you'll do it in a few months, who knows? The point is, there's going to be a simpler solution, and given by the title of this video, you can probably guess what we're trying to do here. But like, how telescoping? How can you possibly telescope it? It's a sum. There's nothing over here. There's plus minus, so we could just cancel stuff. Here it's all plus. Huh? How should we telescope this? First thing to do is look for a pattern. And if you're good with numbers, you'll probably realize that 6 is 2 times 3. 12 is 3 times 4. 20 is 4 times 5. 30 is 5 times 6. So on. 72 is 8 times 9. Wow. Isn't that cool? Always look for patterns. Okay, but we've got this. That's still not telescoping. Well, here's the clever part. This first term is 1/6, right? Now, for stuff to telescope, we have to have something minus something else. We can't just keep adding things. Nothing's going to cancel. I mean, it's all positive. We have to have something positive. We have to have something positive minus something else. But so can we maybe rewrite this in terms of something minus something else? So of the form a minus b, let's say, where a and b are fractions. 1/6. I mean, what other fractions have 6 in their denominator? I mean, 2/6, 3/6, 4/6, 5/6. Those are a few. 4/6 is nothing but 2/3. So we could do something like 2/3 minus a half. Oh, also, notice how this is half, this is a third, this is 2/3, just like that. So we could form 1/6, 2/3 minus a half, but that's kind of strange. I mean, 2/3 minus a half. Any other possibilities you might see? 3/6, 1/2, 2/6, 1/3. It's also half minus a third. Interesting. 1 over 2 times 3 equals half minus a third. And that makes a lot more sense because we've got a 2 here, a 3 here. Okay, that's intriguing. Anything else? Okay, what about 3 times 4? Can we rewrite it in a similar fashion? Is 1 over 3 times 4 equal to a third minus 1/4? Is the question we're trying to ask here. And the answer is, indeed it is. 1 over 3 times 4 equals 1/3 minus 1/4, right? This is 4/12 minus 3/12, so 1/12. Okay, 2 examples. Now, can we generalize it? Is it true in general that 1 over n times n plus 1 equal to 1 over n minus 1 over n plus 1? If this were true, we would that would make the expression we needed, right? For telescoping, we can't just keep adding. We need to have add, then subtract, add, then subtract. So is this expression true? Then we would be able to get that subtraction we really needed. And it turns out this is indeed true. 1 over n is n plus 1 over n times n plus 1. 1 over n plus 1 is n over n times n plus 1. And this simplifies to 1 over n times n plus 1. Aha! So we can always rewrite this as this. So then we just have that 1/6 plus 1/12 plus dot 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 till 1 over 72 is just half minus a third. That's 1/6. 1/12 is a third minus a fourth. 1/15th, or sorry, 1/20th is 1/4 minus 1/5, right? And so on all the way till 1 over 72, 1/8 minus a ninth. Cool, and now, is there any telescoping we can see? Of course, plus a third, minus a third, minus a fourth, plus a fourth, minus a fifth, plus a fifth. Of course, we can't see it here, all the way until minus the eighth, plus a eighth. So we're just left with half minus 1/9. And now we get to find a common denominator. Oh, whoops, I'm blocking. So just to summarize, we found this expression, 1 over n times n plus 1 is 1 over n minus 1 over n plus 1, which simplifies to 1 over n times n plus 1, right? And then we plugged it in over here, to get this really neat telescoping, and now we're left with 1/2 minus a ninth. Isn't that brilliant? And now we can find a common denominator, which is 9 over 18th minus 2 over 18th, 7 over 18th. By the way, for those of you who were trying to find a common denominator for this expression in the beginning, are you done yet? I guess it's probably not, which is why telescoping is so powerful. Telescoping, think about it. You made this giant 1/6 plus 1/12 plus 1/20th, so on, into just half minus a 9. That's the power of telescoping right there. And now let's see another example of telescoping in action. Okay, this one is 3/4 times 4/6 times 5/8 all the way till 10 over 18. And if you don't see the pattern, the denominator is just the numerator times 2 minus 2. So 4 times 2 minus 2, 5 times 2 minus 2, so on. Another ugly fraction and a very not great approach would be to multiply all the numbers in the top and multiply all the numbers in the bottom. Yeah, we're definitely not doing that. Telescoping is the title of this video, so this time though, instead of telescoping adding and subtracting, we're telescoping multiplying and dividing. So immediately right off the bat, you can see, oh, these two cancel, but that doesn't really help that much, does it? Because after that, there's really nothing else that you can see off the bat that immediately cancels. And just because there's only 8 terms, we might as well write them all out, but that still doesn't leave it to be that simple. Oops, this should be 12, 9 over 16, 10 over 18. So I've written all 8 terms now. This looks pretty ugly, doesn't it? So first of all, there's some fractions we can definitely simplify, right? 4/6 is the same thing as 2/3. 6 over 10 is just the same thing as 3 over 5. 8 over 14, 4/7. 10 over 18 is the same thing as 5/9. And now, if you have a good eye, you'll notice something really cool. And I'll give you a moment to think about it. Is there any clues to telescoping you can see right off the bat? Analyze this expression very closely over here. I'll give you a hint. 3/3. Okay. 5/5. Okay. 7/7. 9/9. I think you're seeing 3/3 cancel, 5/5 cancel, 7/7 cancel, 9/9 cancel. Wow. So that leaves 2/4 times 3/8 times 4/12 times 5 over 16. We just literally made this expression half as complicated with a simple step, just like that. And the crazy part is we're not even done yet. These 4's cancel, and now 12, 3, we're left with 4 here, 4, 2, 2 here. Literally everything just cancels, and we're left with 5 over 8 times 2 times 16. That's 16 times 16, 256, and that's our answer. Wow. And actually, it turns out, in general, this is true. If you have, let's say, something a over, or let's say a over 2a minus 2, and a plus 1 over 2 times a plus 1 minus 2, where a is odd, this is equal to a plus 1 over 2a, where a is odd here, we end up getting that a over 2a minus 2 equals a plus 1 over 2a, and from here these a's just cancel like that. Or, sorry, from here we can see that because we said that a was odd, let me write that down. A odd, a plus 1 is even, right? So we can rewrite this as a plus 1 over 2 over a, and now a's cancel out, and we're left with for multiplying these, we're left with the fraction a plus 1 over 2 over 2a minus 2. So this property where we could just cancel like that and get this expression here, 3/8, that is indeed true for all values and not just these small ones that I showed. And another thing you might be able to notice is that the denominator over here is just 4 times the numerator minus 4. So 4 times 2 minus 4, 4 times 3 minus 4, 4 times 4 minus 4, 4 times 5 minus 4. Another really cool pattern, isn't it? And that's true because of the reason we just saw here. So another example showing how powerful telescoping is. And to see telescoping, just have to be looking closely and carefully, and then just watch as things just cancel. Another example, here we come. Suppose x1, x2, and this should say x of 2022 like that, is a sequence of real numbers such that x1 plus x2 equals 1, x2 plus x3 is 2, x 2021 plus x 2022 is 2021, and x1, x499, x999, x1501 is 222. Find the value of that. Why is this in telescoping? Isn't this a equation problem? Why is this in here is it in the wrong chapter? You'll see in a few seconds, or maybe minutes. X of 2022 is kind of like our unknown. So let's say we have x of 2022. Let's call it the same variable because it's our unknown. And it's often a good strategy. Let's say it's a. Okay? A. So a strategy would be to look, if this is a, maybe can we express this in terms of a, we can solve for a. But how do we express these in terms of x of 2022? So to do, let's say we want to express x of 1501 in terms of x of 2022. How would we do that? We have these equations, so we probably should be using them, right? So to express this, let's say we want to, if we can find x of 2022 minus x of 1501, then we would have a way to express this in terms of x of 2022. And now that I think about it, it may just be easier just to let it be x of 2022 instead of a, but it doesn't really matter. Either will work just fine. So if we can find this expression, x of 2022 minus x of 1501, then we can express x of 1501 in terms of x of 2022, right? Because if this is equal to some constant, then now we have x of 2022 equals x of that thing plus constant. So is it even possible to find this constant? Okay, so the key idea here is we have this expression, x of 2022 plus x of 2021 equals 2021. And now the key idea here is we can subtract x of 2021 plus x of 2020 from this expression. Okay. So what would that give us? This is equal to 2020, remember? So that's equal to 2020. We subtracted those expressions, we're going to get x of 2022 minus x of 2020 is 1. Okay, that's cool. Right? We get x of 2022 minus x of 2020 equals 1. So that gives us, that gives us one property that maybe is useful, but that's not enough to find this quantity we're looking for, c. Let's try it again. Maybe this time let's subtract x of 2021 plus x of 2020 minus x of 2020 plus x of 2019. This gives us x of 2021 minus x of 2019 equals 1. Okay, is this always true? We can do the same thing. X of 2020 plus x of 2019 minus x of 2019 plus x of 2018. That says that x of 2020 minus x of 2018 is 1. Okay, it seems like this is true for every possibility between two consecutive values, and that is between values that differ by 2. Sorry, and that is indeed the case. Okay, so what should we do from there? Well, the truth is, it actually won't be that simple to find the value of x of 2022 minus x of 1501, because all the expressions give us a difference between terms that are differed by 2. So x of 2022 minus x of 2020, for example. It's not easy to find x of 2021 minus x of 2020. So what we instead will do for now is we will try and relate all of these with each other with x of 1. Let's see that. Let's say x of 1 equals, let's say x of 1 is just x of 1, right? X of 499 is x of 1. Well, notice how from this first equation we have x of 2022 equals x of 2020 plus 1. So essentially, if you increase your thing by 2, it goes up by 1. So x of, how many times do you have to go up by 2 to get from 1 to 499? You go up, well, the difference is 498 divided by 2, that's 249. You go up by 2, 249 times, so this is x of 1 plus 249. Okay, and similarly, x of 999 is just going to be equal to x of 1 plus 998 divided by 2, right? Because there's 998 differences between 1 and 999, and 998 divided by 2 is 499. Let's erase this. X of 1501 equal to x of 1 plus, we're going up by 1500, but in the subscript, right? So remember, for every 2 we go up 1. So plus 750. Right. So then we're looking for x of 2022, however, right? In terms of these variables. So from here, we can easily find x of 1, right? We can find x of 1 because x of 1 plus x of 499, which is x of 1 plus 249, plus x of 1 plus 499, which is this term x of 999, plus x1 plus 750, which is this term here. This is equal to 222. So we can solve for x of 1 now. We would get that 4 of x of 1 plus 249 plus 499 plus 750, whatever that is going to be equal to. And there's a neat little shortcut you can use. 250 plus 500, 250 minus 1, 500 minus 1 plus 750. That's 1500, 1500 minus 2, 1498 equals 222. And we can move this out of the way. From here, we can see for x1, equal to 222 minus 1498, which is negative 1276, right? We're just subtracting 1498 from both sides. And then from here we get x1 equals negative 319. But now what? We need to find x of 2022. So the key idea here is now we know the value of x1, we can plug it in here. Negative 319 plus x of 2 equals 1. And the reason we do this is because the key hurdle that we could use to finding this minus this or something like that was that this was even, this was odd. But now we know that all the odd values essentially, we can use that to find x of 2, and then we can work our way up to x of 2022. From here we get x of 2 is 320. Right? Okay, and now what we must do is see that x of 2022, notice how it goes up by, remember, after every 2, the x value goes up by, it increases by 1. So x of 4 minus x of 2 is 2, x of 6 minus x of 4 is 2. Every 2 we go up in the subscript, we go up by 1 for the x value. So x of 2022, it goes up 1000 or 2020 in the subscript, but because every 2 we go up, we increase the value by 1. Because we went up in the subscript by 2020, our value increases by 1010, which is 1330. So that is going to be our answer for this problem over here. So the main idea was telescoping over here. And then once we did telescoping, we tried finding x of 2022 minus this, but we realized the odd even hurdle. So we instead found everything in terms of x of 1, solved for x of 1, then plugged it in, and then found x of 2022 by our same fact. So the main fact was noticing these are giant expressions, telescope, and that's always the case. So whenever you have problems that are just too complicated, just make them cancel each other out. I mean, that won't always work, but it's worth a shot. And you can find all these practice problems, which can give you more practice with this amazing technique. Link in the description. For the Mastering AMC 8 book, it's completely free. And we're going to move on to geometry, and we're going to talk about some really cool concepts in geometry and how to apply them, like similar triangles, 3D geo, and many more topics. You can check that out in the next video, which will be linked right over there. Thanks for watching.